Hello, this is the second lecture for Module 7, and what I've done is I've separated some math problems out from the regular lecture so that it's a little more digestible. And we're going to cover some topics in sedimentation and flotation that you may see take the form of math problems in your certification exams, and you will get the ample opportunity to do a few of these problems on your homework set for this module. So I did include the percent efficiency for a clarifier and the detention time background, the formulas, and a couple example calculations in the Module 7 lecture. But when I started looking at the lecture, it seemed like it was dragging on a little too long. So I said, I'm going to separate the three metrics for the clarifier and sedimentation basins separately so that Module 7 wouldn't be too long and so that you get a really good explanation of these metrics and how they're used, how they're calculated. The first is what's called the Weir overflow rate, WOR, and then we have the surface loading rate, SLR, also known as the surface settling rate, or SSR. And I did not use an acronym for solids loading rate because if I did, it would look like surface loading rate. So I'm just going to call that the solids loading rate, okay? What I will once again state is that the Ragsdale Manual's mathematics chapter is chapter 17, and it walks you through every single problem type that you will see on the certification exams. So I strongly recommend you take a look at that. That's just my perspective, my opinion. It's very clear, and he walks you through the examples after he just gives you the concept, okay? So the Weir overflow rate, here's a black and white picture. These little notches are the weirs that we've talked about. And here you have a clarifier, and they're actually cleaning out the weirs here, but the water would typically overflow through this notch into what's called the effluent launderer, or a ditch surrounding the outside of the weir length, okay? And the Weir overflow rate measures the hydraulic loading intensity passing over that effluent weir. And it's going to calculate how many gallons of wastewater or effluent wastewater leaving that clarifier per linear foot of that weir. So gallons per day over foot of weir. Funky unit, but you're going to find we deal with a lot of funky units in wastewater. So why does NMED want the operators to know about this concept? Well, the idea is if we're moving or pushing water over that weir at too fast a rate, it's going to create kind of a pulling effect, and there's a potential for solids to carry over from that primary or secondary clarifier into the effluent launderer and onto the next stage, and that we don't want. And those higher velocities, if they're too high for the exit velocity of the wastewater leaving that clarifier, they can scour up part of that sludge blanket, the top of the sludge blanket, which is composed of lighter biological solids that just settled out, and it'll drag them into the effluent launderer. And if it's in the secondary clarifier, you're going to have an instant permit violation because you're going to be discharging solids, and you don't want that. In addition, keeping that weir overflow rate low is going to make sure that you have a calm water distribution across the basin, and it's going to prevent short circuiting. So the slower we move the water through or into the basin and push it out through those weirs, the slower that velocity, the less opportunity and the less likelihood that we're going to have short circuiting take place. And let's go to the next slide here. The regulatory guidelines, what we're shooting for are 10,000 to 14,000 gallons per day, that's GPD, gallons per day, per foot length of weir. So gallons per day a foot, 10,000 to 14,000 for a standard design flow. The peak, the most you ever want to go is 20,000 gallons per day per foot, and that's for larger systems only during peak hours. So you want to keep these fairly low. Okay, and think about that 10,000 to 14,000 gallons per day. That's not a lot per foot. That's not a lot when you consider some of these plants are taking an inflow, an influent of 1 million to 3 to 4 million. In case of Santa Fe, 6 million gallons per day are coming in. So 10,000 to 14,000 gallons per day overflowing per foot of weir, not a huge amount. It's fairly slow moving effluent leaving the clarifier. So the effluent weir, like I showed you in that photo, it's a V notch typically, and that V notch from the height of the weir down to the depth of that notch is 2 to 3 inch deep, and it's triangular cuts, and those notches are every 8 to 12 inches in spacing. And the launder trough, those are channels underneath or alongside outside the weir perimeter, and that's where the outflowing or overflowing effluents gathered up and sent to the next treatment stage. Uh, Determining the weir length, again, we've talked about two types of weirs, of clarifiers or basins. We've talked about a rectangular basin or a tank, and then we've talked about a circular tank. So the length of the weir for a rectangular basin, we'll see it on the next slide, it's just the width of that rectangular weir, because we have the influent coming in and traversing through the rectangular basin and then leaving on the other side. So that's why I say it's really only a straight line, or the width of that basin. Okay, and the circular tanks, though, the weir surrounds the entire basin, so it's the perimeter or circumference, the outside length of that circular basin, that is the weir length. And let's take a look at that. Okay, so for a rectangular basin here, we have inflow or influent coming in, and that influent is going to move from left to right, and it's going to eventually leave the rectangular basin on the right hand side. And in order for the effluent, the treated effluent or the cleared or supernatant water to leave the weir, it's going to take this exit, this weir that's across that one dimension, that width of the rectangular basin. Whereas for a circular basin, the weir is going to be all around that basin. Okay, so that's the entire length of that weir, and the water is going to overflow, or the decanted or supernatant liquid portion is going to flow into that launder trough, which is just a circular ditch on the other side of the weir. And here you go. This is the clarifier launder and overflow design. This one shows a U-type notch, which is flat on the bottom, but you're very rarely going to see this. You're typically going to see the V-notch weir. Okay, so just to give you an idea of the dimensions for that weir. Okay. Here's a little more detail on the weir. So here, for example, on a rectangular basin, you basically have the wastewater coming in. It's the supernatant. You can have a scum baffle, and the weir plate, the effluent is going to be decanted, or the supernatant is going to go over the weir plate, and there's a little effluent launder, which, like I said, it's just a little ditch. Okay, that's all that is. And on the V notch for this, there's a plate that can move up or down. So it can move down, which would allow more flow to leave at a quicker rate, or it can go up. So you're basically raising the water level, or wastewater level, in that rectangular basin. Now on the circular clarifier, here's the V-notch weir. See that little, looks just like a V, and every 8 to 12 inches you got a spacing of it, and it's a 360-degree exit of the supernatant or cleared up effluent. And recall that for a circular clarifier, we have the wastewater coming into the center of that clarifier. If it's a circle, it's being moved in an upward manner, or upward trajectory and velocity, and it hits a baffle and it comes down slowly, and then it just spreads out to the edges of that circular basin. Okay, and this, like I said, is just a schematic to give you an idea of what the weir looks like for both a rectangular on the left hand side and a circular on the right hand side. Okay, so we want to become a bit more familiar with the geometry of a circular weir. Okay, the reason I'm telling you this is there's a little bit of a math trap on NMED exams. So you're very rarely, if ever, going to be given the entire weir length. Typically, you're going to be given a circular weir with a diameter, and they're going to expect you to calculate the circumference of that shape, which is the perimeter all the way around the circle, the path all the way around the circle. That's the circumference. So you can use, looking at a circle, here's the diameter D, and here's the radius R. The radius R is from the center to one side, whereas a diameter is from one point on the circle to the opposite point, and it passes through the center. Okay, that's the diameter. So the weir length is basically the circumference, and that's pi, or 3.14 times the diameter. If you really, really like using radiuses, it's 2 times pi times the radius. Same thing, okay? The diameter is twice the length of the radius, so 2r is going to equal d diameter in this case, okay? And d is the diameter of the circle, r is the radius, and then pi, you can just use 3.14. So that's how we calculate the length around that circular clarifier. Okay? And then the weir overflow rate, all we're doing is we're taking the influent flow rate, what's coming into the clarifier flow rate in gallons per day, and we're dividing it by the circumference of that circle, or the total weir length. That's what we're doing. And the flow up on top, we want that in units of gallons per day. Okay, that's what we want the influent flow rate at. The bottom component, we want that units to be in units of feet. Okay, and the final result for the weir overflow rate is going to be gallons per day per foot of weir. Okay, GPD per foot, but that's what it stands for, gallons per day of influent per foot of weir. Okay, so here's how we would solve a problem for a weir overflow rate. So first of all, if we're given an inflow rate in units of millions of gallons per day, or MGD, we multiply that number by 1,000,000 in order to switch to the standard gallons per day. And then we find the length of the weir, and it's basically, for a circular basin or clarifier, it's the circumference, which is pi times the diameter that you will be given for that clarifier. And then we're simply going to divide this flow in gallons per day divided by the result here, by that circumference, that linear footage. And here's an example. So we've got and this you will likely see like a level 2 exam, level 3 exam. Okay, so the problem statement is as follows. We've got a primary circular clarifier at a New Mexico facility, and it handles an inflow of 1.8 million gallons per day. The diameter of the tank measures 60 feet. Find the weir overflow rate. So the first thing we're going to do, based on our system or solution method on the previous slide, we're going to take that 1.8 million gallons per day, we're going to multiply it by 1,000,000, and we get 1,800,000 gallons per day. Then we want to compute the total active weir length, L, which is basically pi, or 3.14, times the diameter of 60 feet, and that's 188.4 feet. And what that basically means is to take that, it's not going to be a perfect circle, but take the path around that clarifier is 188 feet if you were to walk all the way around that. Okay, so we then look at the division for our weir overflow rate, or WOR. That's this flow, 1,800,000 gallons per day, divided by the weir length, or that circumference of the circle, 188.4 feet. We do that, and our weir overflow rate is 9,554.1 gallons per day per foot of weir. Okay. Now, what does this mean? Well, from a compliance perspective, if you recall the ratios we looked at earlier, the ranges we looked at earlier, that 9,554 gallons per day per foot, it's a little under the standard operational threshold of 10,000 gallons per day per foot. So what that means is we're going to get optimal, or really good, particulate settling dynamics, because we're moving that wastewater fairly slowly through that primary clarifier. We're allowing settling to take place. Okay. Let's now switch gears to the next metric or performance measure of a clarifier, and that's the surface loading rate, or also known as the surface settling rate. Those are interchangeable, okay? So the concept is the surface loading rate or surface overflow rate uh, measures the upward velocity of wastewater within a clarifier. And we're looking at how many gallons of wastewater pass upward through the square foot of the tank surface area every single day. And why are we interested in this, or why is NMED interested in making sure operators understand this? Well, what's going to happen is, recall that particles in a primary clarifier settle down due to gravity, and that water is going to move upward and exit over the weirs. Okay. Well, if the upward water velocity is faster than the downward settling velocity of those particles, that sludge or flocculate that's coming down, the particles can be carried over, they can escape into the effluent launder. And again, automatic permit violation, automatic problem with your process down the line. Okay. So we're monitoring as operators, we're monitoring the surface loading rate to ensure water is going to move slow enough to let the solids settle out completely in that clarifier. That's it. We're just looking at the performance measure of how we're letting solids settle out in that clarifier. The guideline for a primary clarifier, we want 600 to 1200 gallons per day, and it's per square foot because we're talking about an area. And we typically want about 800 gallons per day per square foot, and that falls within this range. But here's the range for a primary clarifier. It's even lower for a secondary clarifier with activated sludge. Recall the primary clarifier, our sludge is raw sludge or primary sludge. Secondary clarifier is biologically active sludge, where we have microbes in there that we've set up to metabolize that waste in the sludge blanket. Okay. Well, for a secondary clarifier, we want it lower because we have, as you recall, we've talked about this in the last lecture in this module, that biological flock is like a snowflake, a heavier brownish snowflake coming together. They're quite delicate, and we want to make sure that any water or wastewater moving through this process is moving fairly slower because these flock settle out much slower. So we don't want to disturb those. We want this flock to settle out to the sludge blanket. So that's why a secondary clarifier's surface loading rate is much slower than a primary clarifier surface loading rate. That sounds like a good test question, doesn't it? Just so you know, it is a good test question. You might see it on a level 2 or level 3 exam. Okay. So another trap, NMED in their exams, they're never, ever going to give you a surface area for a clarifier. They're going to give you dimensions, whether it's rectangular and you do length times width to get the surface area, or for a circular clarifier, they're going to make you find the area of that circle. And it's all based on the tank shape, but they're never going to give you just, here's the surface area of a clarifier. No, they're going to give you dimensions and make you figure it out. Okay. One thing to remember, and this has tripped up some people, it sounds like it shouldn't, but it does. Ignore the depth of the tank. You're not interested in it. You are only looking at the surface footprint, the plan view, the arching view from the top looking down. So for a rectangular basin or clarifier, you're looking at length times width. For circular, you're looking at the surface area of that circle, which is pi r squared. Or we're going to actually look at an easier way to deal with things, because you're never going to be given the size of a clarifier by its radius. You're going to be given the diameter of the clarifier. So you don't want to deal with the radius. You just want to plug and chug. And for the rectangular surface area, it's length times width, length in feet, width in feet. That'll give you area in square feet. Well, for a circular tank area, which is the most tested, your area in square feet is going to be 0.785 times D in units of feet squared. So you don't have to change anything. And this 0.785 is pi over 4. And I'm not going to give you the derivation of how this works compared to pi r squared, but it does work. And here's the thing. You can use pi r squared but you're not going to be given a radius, so the odds of you making an error by using a diameter instead of a radius is pretty big. So you want to use, for your basic calculator, 0.785 times diameter, and that's going to give you some really quick results. You're moving forward. Think about it. For a 6-hour exam, you've got 120 questions. You want to move forward quickly. You want to save as much time as you can while you move forward. So rather than play with diameter versus radius, what have you, trust me, you're going to get your dimensions for a circular basin in units of a diameter, feet for a diameter, okay? So instead of messing with diameter, turning it into radius, then saying pi r squared, just enter into your calculator 0.785 times diameter. There's your surface area. It's that simple. Get into the habit of doing that. It will save you time. It will eliminate mistakes. Sounds foreign to you right now, perhaps, but trust me, once you get used to it, it's going to make life a whole lot easier for you, okay? So the standard formula for the surface loading rate, it's the influent flow rate, what's coming in, divided by the tank surface area. And the top influent flow rate, the numerator of this ratio, it's got to be explicitly in gallons per day. So again, if you get millions of gallons per day, you multiply it by a million to get your gallons per day. And the tank surface area, you will be given the dimensions of that clarifier in units of a diameter in feet. And your area, if you do 0.785 times D, that's going to be square feet. Okay, so gallons per day per square foot. That's what you should end up with. If you are not ending up with those units, you need to practice some more. You need to make sure you know what you're doing, because this is going to come at you hot and heavy on an exam, and you don't want to doubt yourself. You don't want to create more problems and waste time. You want to be confident and move forward with this and save yourself time by being efficient. Okay. So there's a 3-step solving process or solution process to surface loading rate. The first step is to convert that flow. If you're given in millions of gallons per day, multiply it by a million to convert it to gallons per day. Okay, step 1. Step 2, compute the surface area of the tank using the dimensions provided. Again, you should be getting circular clarifiers, not rectangular. Be aware, length times width, that's the surface area of a rectangular basin. Again, we've talked about how to compute the area of a circular basin, but that's what you want to do. And then you simply take that ratio for surface loading rate, the total daily gallons of influent divided by the total surface area in square footage. And here's an example. Here's our problem statement. A secondary circular clarifier has a diameter of 70 feet and treats a daily design flow of 1.5 million gallons per day. What's the calculated surface loading rate? Well, the daily influent, we get it in 1.5 mgd. We want to go to gallons per day. So we take that 1.5 mgd, multiply it by a million, we get 1,500,000 gallons per day. The tank surface area, it's a diameter of 70 feet, so it's just 0.785 times 70 times 70, diameter times diameter. You do that, you get 3,846.5 square feet. You take the 1,500,000 gallons per day in the numerator, and that's in gallons per day. And on the bottom is the area, 3,846.5 square feet. You divide and you get 390.0 gallons per day per square foot. And what does this mean when we go back to the criteria we talked about, regulatory criteria? It's really a pretty good metric. We're meeting that metric that's spelled out fairly well. That result of 390 gallons per day per square foot for a secondary clarifier, it's well within this range. It's on the lower end of the range. So what that means is our flow is really calm in an upward velocity as it's coming into our clarifier. So it's not going to wash away or come close to washing away that biological flock in the secondary clarifier that we talked about. So it's a really good result here, okay? So let's look at solids loading rate now. This is the third metric we mentioned. Solids loading rate, it's going to calculate the actual weight of dry suspended solids applied daily to each square foot of the surface area of that clarifier. It's not hydraulic loading. Okay, when in hydraulic loading, we're looking at only the water or wastewater volume. Okay, this particular metric, the solid loading rate, it monitors the combined impact of the water flow and the solids concentration. Okay, so why are we testing this, or why does an MED want to make sure operators understand this? Well, in an activated sludge system, okay, that secondary clarifier is going to do two things. It's going to clarify the water from the influent coming in, but you remember with the secondary clarifier, we're actually recirculating a portion of that sludge from the bottom of the clarifier. We're sending it back into the inlet or the influent of that secondary clarifier. That's our return activated sludge, our recycled sludge. And we're interested in doing that because we want that biomass of all those microbes. We want them to come back into a high dissolved oxygen environment where they're activated. They're hungry and they're going to munch away and metabolize that organic waste. Okay. So that's why what we're looking at here, clarifying the water and thickening the solids with that RAS, that return activated sludge. Now, if we put too many pounds of solids into the clarifier, the solids are going to build up, and that sludge blanket's going to build up faster than we can remove it. So we're eventually going to fill up our secondary clarifier, and we're going to have an overflow problem with our solids, okay? So we don't want to do that. So what'll happen is if we do that and we get a blanket overload, the sludge blanket goes to the top, spills over the weirs, and again, you're eventually going to discharge solids, and that is a big no-no. The EPA will come at you quickly, harshly, and you might want to update your resume if you're in charge of that shift and that happens, okay? So regulatory guidelines for a secondary clarifier with activated sludge, your solids loading rate is going to be 12 to 30 pounds per day per square foot. With nitrification, where we're looking at removing nutrients, it's going to be 24 to 35 pounds per day per square foot. And that higher loading is due to different settling characteristics due to those nutrients. Okay. And as I mentioned earlier, wastewater treatment, it uses some pretty funky units, but just focus on what you're looking for and you're going to be okay. As I mentioned in the first portion of the Module 7 lecture, please do not worry about trying to memorize these formulas. You want to know what they mean. You want to know how to use them, where practice helps. But you're going to be given a formula sheet by the Environment Department when you take your certification exam. And I will, again, find that in the next day or so and post that to Module 7, okay? Or I may put it in a separate standalone module. But I want to make sure you're aware of this. And units, they're going to do nothing but help you figure out what you're doing. Here's a hint for you. If you're not very confident what you're doing, and I want you to be confident, I want you to do enough practice problems so you feel good walking into that exam. But take a look at the units in your answers, in your multiple choice answers. That'll give you a guideline on what you're hoping to do. Okay, so in this case, if we had a solids loading rate question, each of the answers is going to give you units of pounds per day per square foot. And as we're going to find out with our standard formula, that's actually going to point you in the right direction on how to use the formula as well. Okay. So there's a two-step formula approach here for a solids loading problem. And the idea is we've got to do two things. We've got to, for the denominator, we have the surface area we're going to be looking at of the clarifier. The numerator, though, the top of that fraction, we're going to go back to our pounds formula. Okay, we can look at it as a Davidson pie chart, what have you, if that helps you, and I'll explain that in a bit. But that pounds formula is simply pounds per day is going to be equal to the flow in, we want this in units of millions of gallons per day, not in gallons per day, MGD. And then the MLSS, that's the mixed liquor suspended solids concentration in milligrams per liter. Mixed liquid suspended solids. That refers to the biomass in the secondary clarifier. That includes sludge plus the microbial mass, the biologically active portion of the sludge in the secondary clarifier. The MLSS, that's where all the magic happens. That's where the bugs, the microbes are measured. The concentration of them are measured. So you're going to see MLSS concentrations of a couple of thousand milligrams per liter on up. So again, the MLSS, that's mixed liquor suspended solids, that represents the microbial fraction or the microbial concentration of the biomass in that sludge, okay? And then you're going to multiply this by this constant of 8.34, and that 8.34 is basically pounds per gallon. That's the density of water in English units, okay? So here's something else to realize during an exam. If we're talking about a secondary clarifier, this flow here, okay, it's got to include the influent flow and I say this to stress it, and the return activated sludge flow. They're both coming in. Okay, that return activated sludge, we're pulling that sludge off the bottom of the blanket and we're recirculating it and introducing it back in the influent area of the clarifier, okay? That's the RAS. So we've got to account for the influent coming in plus that RAS, okay? Now for a primary clarifier, you're just interested in the influent coming in because you got no recirculated flow in a primary clarifier. Here's what the solids loading rate formula is. It's just the solids in pounds per day divided by the total tank surface area. And a reminder, for a circular tank area, that's 0.785 times diameter in feet or diameter squared. Okay, that's the denominator here. And the solids, we are going to use that pounds formula of flow in millions of gallons per day, inflow millions of gallons per day, multiplied by the MLSS concentration in units of milligrams per liter, multiplied by 8.34. Okay. So there's 4 steps to solving this type of problem, a solids loading rate problem. We have the total flow, and that's where we're going to combine the influent flow plus the RAS flow, and this is both in millions of gallons per day. And again, here's our note. You only add the RAS flow if you're looking at a secondary clarifier. For a primary clarifier, we're just interested in the influent flow. Okay. Step 2, find the total pounds by applying the pounds formula. And here it is. Pounds per day is flow in millions of gallons per day times the MLSS concentration in units of milligrams per liter times 8.34 pounds per gallon, or just 8.34. Okay. You calculate the surface area in square feet, and then you just divide the total pounds in step 2 by the total surface area calculated in step 3. Okay. And here it is again. Top component, total weight, explicitly pounds per day. That's what you want. The bottom component, explicitly square feet. Your final result of your solids loading rate, pounds per day per square foot. Okay. Let's take a look at an example problem. We've got a secondary clarifier. It's circular and it has a diameter of 60 feet. The plant treats an influent of 2 million gallons per day, and it's got a RAS rate, return activated sludge flow rate, of 0.5 million gallons per day. The mixed liquor suspended solids entering the clarifier is 3,200 milligrams per liter. That's the biomass, the microbes coming in from the RAS, from the recirculated sludge. Okay, we want to find the solids loading rate. Well, the first step, calculate the total flow. What's entering the clarifier? That's 2 million gallons of influent, 2 million gallons per day, plus 0.5 million gallons per day of RAS, return activated sludge. Total inflow to that clarifier is 2.5 million gallons per day. Okay. Then we're going to calculate the total pounds of solids that we have in there per day. That's this flow rate, the combined total flow, 2.5 million gallons per day multiplied by the MLSS concentration, 3,200 milligrams per liter multiplied by 8.34, we come up with 66,720 pounds per day is entering that secondary clarifier. That's a lot of mass. That's a lot of microbes, right? Biomass coming in, 66,720 pounds of biomass or microbes entering the secondary clarifier per day. Okay. So we then compute the tank surface area. And again, the area is just 0.785 times diameter in feet. So 0.785 times 60 feet times 60 feet, 2,826 square feet. Okay. Hopefully by now you're seeing how quick you can move with using this approach, vice pi r squared with your calculator. And then your solids loading rate, you take that 66,720 pounds per day for your solids, and then you divide that by the area you came up with of 2,826 square feet. You end up with 23.6 pounds per day per square foot. That's your solids loading rate. Okay, that's the amount of solids per day coming in per square foot of surface area of that clarifier. Okay, so let's evaluate this. That 23.6 pounds per day per square foot, it's acceptable because remember, our range for a secondary clarifier is 12 to 30 pounds per day per square foot. So we're in the middle of that. We're not in the high end, we're not in the low end, we're right in the middle of it. So the clarifier is well sized. It's appropriately sized to thicken the solid load, and it won't cause a blanket washout. So that's what we're looking at. So I've given you the formula of each of the three performance metrics for a clarifier. I've shown you how to manipulate those and what you need to do to get to the components of each of the formula. And then I gave you some examples. So if you have any questions or comments or feedback, please reply to one of the threads that I put up in Module 7, just saying, ask your questions here. Okay. I gave you some mathematical concepts that help you evaluate the performance of both primary and secondary clarifiers. And I know it's a lot of material. It's like I'm saying here, hook your mouth up to a fire hose. I'm going to go full blast. I know I'm giving you a lot of information. There's really no way around this with an 8-week long course. But here's the thing. The reason I'm introducing math now is I want you to see how it fits in with each process we're talking about, number one. Number two, the last thing I want to do is wait till the end of the semester, then spring the math module on you, and then try and just do a power dump on you. That wouldn't be fair to you, and you would not retain the material. So I want to make sure that we go a bit at a time, okay? If you have questions, please ask them in the forum, okay, on the discussion threads. I will be happy to answer them, and I will answer them for you. For your homework, I gave each level questions. I broke it down again into 4 types of questions, levels 1, 2, 3, and 4. I gave each one of you some representative sample problems you could see on your exams. Now, I also gave you solutions to each of the math problems in the module. I did that because I don't want you spending too much time beating yourself up or pounding your head against a brick wall. But I'm going to ask you, please attempt the math problems on your own before you look at the solutions. You're going to get a whole heck of a lot more mileage and value out of your study time and your homework time by doing that. Okay. That's all I have for you on these 3 metrics. One last thing. I did not cover what's called the sludge volume index. I did give you a problem on that. Here's what I'm going to tell you. Take a look at chapter 17 of the Ragsdale manual, which is the arithmetic chapter. It explains sludge volume index there. It's not a difficult concept, but please do take a look at that, okay? And that's all I have for you. I hope you guys are doing well. I hope you enjoy your holiday Juneteenth off. One extracurricular assignment. I love American history. I love local history. And when Juneteenth became a national holiday a few years ago, I decided to look it up. So if you're interested in American history, I encourage you to look up the origin of the Juneteenth holiday. I think you'll find it really interesting, and it'll give you a little better sense of why you have a holiday on June 19th. I wish you guys well and good luck studying. Ask if you have any questions. Please, please, please ask them. You can do it on the threads. You can do it on email. I gave you my cell phone. You can even text me and we'll arrange time for us to talk. Thank you. Goodbye.